ICO 221 VTVM 1949. This video is part of a hobby project with the hope that it could provide useful information. If you see or hear something horribly wrong in what I do, it might be helpful if you took the time to let me know. This is a vacuum tube volt-ohm meter, part of a series of kits made by ICO starting from the late 1940s. According to some adverts collected and available online, this VTVM was developed already in 1949. It might be able to read AC and DC voltage up to 1000 volts and resistance up to 1 gigaohm. With a special probe, it might be able to read DC voltage up to 30 kilovolts. This particular restoration project is about two of these units, one that seems to have been built by the factory, and another one that was clearly built as a kit, which arrived with a broken and unrepairable milliamp meter. The typical VTVM, like the ICO 221, is composed of a double tride, used as an amplifier, and a milliamp meter used to compare the differential voltages at the cathode resistor. One tride is used to amplify the input voltage, while the other is used for making a comparison with the control grid connected to 0 volt. The balancing potentiometer is used every time before a measurement to align the meter to 0 while measuring 0 volt. For the purpose of keeping the milliamp meter aligned to the scale, there is also a calibration potentiometer used to control the current flowing through the meter. This type of calibration would be made only once before making the voltmeter operational to align the instrument to the scale using an external voltage reference. As the actual meter is a polarized mechanical milliamp meter, which could measure currents only in one direction, the direction of the current must be predictable. Looking at the picture, if the DC input voltage is positive, the first tride is traversed by a higher cathode current, which would increase the voltage of the point K1 compared to K2. Therefore, the milliamp meter should be connected so that its positive terminal appears on the side of K1. The picture represents only the basic voltmeter contained in the ICO 221 VTVM with the switches necessary to invert the milliamp meter. For a better meter calibration, there are two different potentiometers, AIR27 for the calibration of positive DC voltages and AIR29 for the calibration of negative DC voltages. To be able to read voltages in different magnitudes, it is necessary a voltage divider made of a sequence of resistors. This schematic diagram represents the DC voltmeter, including the probe. The DC input is composed of a voltage divider made of the resistors AIR31, AIR18, AIR19, AIR20, AIR21, and AIR22. After that, another series of resistors is used to control the maximum current that would affect the vacuum tube grid in case of failure of the insulation. This series of resistors would not interfere perceivably in the voltage read from the voltage divider. For the measurement of AC voltages, the AC input is rectified and then the result is fed to the DC voltage divider. However, the milliamp meter has a different calibration potentiometer, AIR30, and the rectifying circuit contains another potentiometer, AIR5, to be adjusted once to the 0-volt AC. When the VTVM is used as an ohm meter, a battery is used to traverse the resistor under probe with a small current, so that the voltage across the resistor could be read. In this case, the voltage divider seen for reading DC voltage is not used. The AIR12 adjustment is used every time to align the meter to zero resistance at the beginning of the meter scale, shorting the probes together, while AIR28 is used to align to infinite resistance at the end of the meter scale, disconnecting the probes. Finally, this is the full schematic diagram of the ICO 221 VTVM. In the written documentation that is available following the links appearing under the Show More tab, one may also find the full connection plan under the chassis and other details. One of the two units under restoration had a damaged milliamp meter, which has been impossible to repair. For a replacement, it has been found a 500 microamp meter, although not as large as the original one. The original was a 1 milliamp meter, so the new one is more sensitive, requiring the adaptation of some component values. The minimal restoration required by this piece of equipment is the replacement of all capacitors and of the resistors visually in bad shape. However, AIR10 and AIR11 should definitely be replaced, regardless of their appearance, to ensure the possibility to perform the zero alignment. AIR1 might have suffered from overheating, and it is a good idea to change it as well. All other original resistors, unless they are found faulty, might be still okay and could be left in place. In this particular restoration, also the rectifier has been replaced with silicon diodes, a fuse has been added, and also a small light bulb has been put in series with the mains to reduce the chance of future destructive accidents. For the details, see the written documentation. It is very unlikely to be able to find and get this VTVM model with the original test leads, and also these two units arrived without. It is then necessary to build new test leads. The easiest ones are those used for the ohm meter and for measuring AC voltage. They only need a piece of wire connected to a 4 mm diameter banana plug for the common lead and another one connected to a 2 mm diameter banana plug for the ohms AC lead. For measuring DC voltages, a special test lead should be prepared. A shielded cable is required, connected to a 6.35 mm mono jack plug. At the probe end, a 15 megaohm resistor must be added in series to obtain correct readings and to prevent accidents to the operator when connecting it to high voltage sources. The DC volts lead is meant to be used in conjunction with the common lead. This measuring instrument requires an initial calibration that is performed only once, and a measuring alignment that is performed every time before taking any measurement. The initial calibration involves the potentiometers AIR29, AIR30, AIR5, and AIR27. The analog milliamp meter should be mechanically aligned when the unit is still turned off using a screwdriver, so that the meter needle points to the leftmost sign on the scale. Before doing so, the unit should be standing in its operational position. The following steps require powering up the unit first. The unit is meant to work at about 110 volts AC. Negative DC voltmeter calibration. According to the original documentation, the first calibration to be performed is related to the negative DC voltage. Following the suggestion of the original documentation, the unit is set for minus DC volts and 5 volts full scale. Then, the test lead connected to the DC volts jack and the one connected to common are shorted together, and the potentiometer for the zero alignment is adjusted, so that the meter needle reaches 0 volts. With a DC power supply connected to a digital voltmeter, a value around 3 volts is chosen, and the test leads are then connected so that the common lead is attached to the positive output of the power supply, while the DC volts lead is connected to the negative output instead. The calibration point R29 is used to align the meter needle to 3 volts DC on the scale or any other value that has been chosen from the power supply. Positive DC voltmeter calibration. To calibrate for positive DC voltage, after moving the function switch to plus DC volts, the zero adjustment procedure is repeated, joining the DC volts and common leads. Then the DC 3 volts from the power supply is used again, but connecting the DC volts lead to the positive output and the common lead to the negative output. The calibration point R27 is used to align the meter needle to 3 volts DC on the scale. The ohm meter section of the unit does not require a calibration procedure. Before taking a measurement, the ohm meter has to be zero adjusted and infinite adjusted using the two controls on the external panel. AC voltmeter calibration. AC voltage is measured using the ohms AC and the common leads. The function switch is set to AC volts, and for the initial alignment, the range switch is set to 1000 volts. Then the ohms AC and the common leads are shorted together so that the zero adjustment can be used to align the meter needle to 0 volts. After that, keeping the leads shorted together, the range switch is moved to 5 volts, and the calibration point R5 is tuned to get again the meter needle at 0 volts. Then, still keeping the leads shorted, trying other positions on the range switch should not produce a significant deviation of the meter needle from the 0 position. With the help of a signal generator, a 400 Hz sine wave of about 8.49 volts peak to peak is produced to be used as a standard for the AC volts calibration. This value corresponds to 3 volts RMS. With the range switch at 5 volts, the ohms AC and the common leads are connected to the output of the signal generator, and the calibration point R30 is tuned so that the correct voltage is read on the scale of the meter. This concludes the calibration of the VTVM. This VTVM model, like many others, needs a battery for measuring ohms. The battery was contained inside the case and often forgotten for decades. As of today, most cabinets of this VTVM model have suffered from corrosion due to battery leakage. To clean the cabinets of these units under restoration, removing the old paint and the corrosion residues, they have been submerged in vinegar for some days, then cleaned and painted again. Also, the handles have been replaced with modern strong synthetic fabric tape used for bags. This video clip shows the typical usage of the VTVM. The first measurement that is meant to be taken is a low negative DC voltage. The function switch is set accordingly. The DC probe needs to be shorted to the common lead, and then the meter should be zero adjusted. To make sure that the meter needle would not hit beyond the end scale, the range switch is set initially at 100 volts, which is surely higher than what is going to be measured. The measurement shows about 10 volts, therefore, the range switch is now set to 10 volts in scale. The reading is now negative 9.8 volts. The same procedure is then followed for measuring a positive DC voltage. In this case, positive 9.3 volts is read. The DC probe is removed and the AC lead is used instead, repeating the same procedure, but for measuring a low AC voltage from a signal generator. The reading is about 8.6 volts RMS. For measuring ohms, the VTVM is first zero aligned, shorting the leads, and infinite aligned, opening the leads before reading a value. chosen range was too high. Current reading is about 1 kilo-ohms. When the VTVM is not needed anymore, it is always better if the function switch is not set to ohms to avoid draining the internal battery. A high-impedance VTVM is capable of measuring very high resistance values. This model could measure up to 1 gigaohm, even though only with very low precision. This is good enough to test capacitors for electrical leakage. In this clip, a comparison is made with the measurement of a new ceramic capacitor and an old paper capacitor, both with a nominal capacity of 100 nanofarad. The new capacitor charges fast, and the meter needle reaches infinity relatively soon. In comparison, the old capacitor charges slowly and the meter needle stops at about 500 megaohms. Here is the happy restored VTVM couple with repainted cases and new handles.